What is it?
We made an error in the speed, sir. We need to make a course correction.
Granted, so what's the problem?
That's the problem, sir. We need to know precisely where it is to send the command signal. Otherwise, we're interfering with the satellite.
So, you're telling me we need the exact distance of the ship at the moment we send the signal?
Yes, sir. But it's impossible.
We need a solution, now!
But it's impossible, sir. How will we know how much is travel if the speed is not a constant?
Well, looks like we have to pray for a miracle.
You won't need a miracle. This is an example of a real-world problem where integration becomes a powerful tool. But first we have to ask ourselves, what is integration? For that, we have to go back in time.
In the 1700s, Sir Isaac Newton and Gottfried Wilhelm Leibniz independently formulated the idea of infinitesimal calculus. Although Newton is credited for differentials, which he then referred to as the method of fluxions, both he and Leibniz are credited as the ones who formulated the study of integration. They've postulated that the area underneath the curve can be thought of as made up of rectangles of infinitesimal width, which is where the name came from.
But why is finding the area under the curve so important?
That is a good question. You see, when you want to check how much progress you've had over a period of time, you usually multiply the rate of your work, your speed, with the time that has elapsed. This is the principle of speed equation, which shows us that speed is distance divided by time. But what if your speed is not constant?
Changes in speed directly affects progress, and depending on the degree of deviation you have, you will end up with a totally different answer than expected. We first have to understand that calculus, then referred to as infinitesimal calculus, is a tool used to study motion and changes. Newton himself discovered calculus as a consequence of studying heavenly boundaries. So when we think of calculus, it's important to think about changes in motion, so let's apply it here. We're all familiar with functions. An input on the x-axis corresponds to an output on the y-axis. But let me modify the way you think of functions. In here, you see I have a simple function, f of x is equals to 5. That means that my y-axis is equal to a constant, a singular number. But rather than thinking of this as a dot that aligns with y equals 5, think of this more as a straight line from origin going all the way up to 5. This is important for understanding integrals, which you will see later.
When we have a function, we can hypothetically calculate the area by adding up the tiny parts of the function. For example, if we have f of x is equal to 2x, we can find the area under the curve by adding up the y values together. We first need to put boundary, let's say 1 to 5. This is the part whose area we will find. Now, next step is just adding it together. Substitute the x with the numbers on the graph, and we get 2 plus 4 plus 6 and plus 8 and plus 10, which equals to 30.
This is not bad, but there are a couple of issues here. First of all, this is an incredibly simple and small number. A lot of problems tackle way bigger numbers than this, and if we add them manually together, it would take us forever.
Exactly. Another problem, which you will see later, is that this is incredibly imprecise. We're taking out small points of the graph and adding them together. And if we zoom in up, we're taking out a huge chunk of the area.
Not to mention that you take the area of something not by adding them together, but rather by multiplying the two axes together.
So what can we do?
That is where the power rule of integration comes in.
By adding 1 to the exponent of the function and dividing it by the value of the exponent plus 1, you will get the integral of the function. So for the function 2x, you will add an exponent on the x, which will make it 2x squared, and you will divide it by 1 plus 1, so 2 because we take the exponent and use it as a value for which we will use to divide the function with. When you have that, you will have the final answer 2x squared over 2, which if we simplify by cancelling out the fraction, we will get x squared. After this, you will simply add a c as your constant.
Is that simple? Yes, that's your integral. Well, not one. This the indefinite integrals. To get definite integrals, this add boundaries.
By adding an upper and lower boundary on the integral sign, you are essentially saying that you want to calculate the area from that range in the x-axis. For example, you want to figure out the area from x equals 2 to x equals 7. What you will do is substitute the x for the upper boundary. In this case,
Is equals to 49. And you subtract it, those squares, it means 4. And you get 45. Which means that the integral of our function 2x, where our boundaries is 2 and 7, is equals to 45.
Happy to the constant.
That's a good question. When it comes to definite integrals, we no longer add the c, the constant, because in definite integrals, the constant cancels out. We only use the c in indefinite integrals.
So, what about our ship?
Your ship's accelerating exponentially, isn't it?
Yes.
So the function of the ship is x squared.
Plug the values in, fast, go!
Hang on!
What?
I just noticed, when you're integrating a function, it looks a lot like differentiating it, but in reverse.
So through that, huh?
Yeah, but well, I guess that's why they call it an antiderivative. You got something else? Something a little bit more difficult? Enlighten me.
Okay, there's a more difficult version. So here, we have a trinomial problem. 9x raised to 5 minus 4x cubed plus 7 and dx.
The first step is to get each other integrals respectively. So first, we have 9x to the 5th power, then negative 4x cubed, then plus 7. The next is separate the constant, this one, right here. Add 1 to the exponent and give it as the denominator. X raised to 5 plus 1. Then this 5. Then repeat it until you finish integrating all items. Next is all exponent is added by 1, so plus 7 x, then write constant. Lastly, look if there is any room for simplifying. For example, this 9x to the 6th power over 6 can be divided by 3, and the 4x to the 4th power over 4 can be divided by 4. Plus 7x, then don't forget to write the constant. So this our final answer.
Now, we know how to deal with problems using integrals involving trinomials. But what if our problem is like this? As you can see, our problem involves fractions. It may look hard and tricky at first, but if we follow the steps, it will be easy. Our first thing to do here is simplify the fraction by dividing both sides to its common factor, which is 5. And then we will get 2 over x to the power of 3. We will turn the fraction into its improper form by moving the x to the power of 3 up to its numerator, and then turn the exponent into negative. After that, we will add 1 to its exponent and use it as our denominator. Then, we further simplify the fraction until we get its simplest form. Divide both sides by 2, cancel it out, and then we will get x to the power of negative 2. Turn it into a proper fraction, and then add c to represent the constant.
Well, I guess that's all.
Your journey with us ends here. This you must venture alone.
Wait, that's all you're teaching us?
Well, yeah, you can take it from here.
Well, I'm sure you'll know your way.
Thank you for your help.
Till next time.